Hi guys, this is John. Welcome back to the system design interview sessions. Today we are going to walk through the Haystack white paper. Haystack is Facebook's photo storage, and you can imagine the volume, the traffic behind the scene. And quote from the paper, there is a certain patterns for the photos on Facebook where data is written once, read often, never modified, and rarely deleted. So today we're going to see how it works and also walk through some key concepts that could be useful in the system design interview. Just to remind, the video series is with a strong focus on anyone's upcoming system design interviews. If you would like to learn in more details, please let me know. We can discuss in more details about how each component works, how each concept with implementation details. Because to fully analyze with such a white paper, it requires, if not weeks, but at least days of work. There's so many different technical points we can discuss. But today, let's try to keep at a certain level that will be useful and beneficial for your upcoming system design interviews. And I would recommend if you read the paper at least once before coming to view this video, it will be like more helpful to help you understand some of the key component. So let's get started with the first approach Facebook or Meta took when it comes to photo storage. The first one is simple enough. I didn't draw much diagram or graph here. So it's simply AI-based as network attached storage, which can expose some storage of folders, and then the file server can mount it to its local folder. So you can imagine this file servers or web server with extended storage provided by the network file system. So it is as simple as that. Photos are stored as photos, just like we did on our personal laptop or PC. You store it on the folder and then the file names ABCD. Then when the clients upload or read, it goes through the file server, and then the rest is typical systems. File server, of course, stateless, and upload the files with user information without any metadata for the photo in the separate storage. So metadata. Like file ID, size, type, like there's some thumbnails. That's typically four types of file for each photo uploaded by clients stored at Facebook site. You can go into details later, but here you can imagine it's as simple as straightforward as that. File uploaded, store metadata, store in the file system, provided by nice appliance mounted to the file servers through network file system. So it's basically the first design. Then it comes to the bottleneck. Okay, here's the attention point. When you are talking about system designs, what you want to improve that, but you need to have like a baseline based on what point I want to improve. Is that improvement or solve a problem, or exactly why do you want to make changes to the existing system? So in this case, it's a valid reason. So we experience or might experience a bottleneck storing and reading photos in this way. The bottleneck is about like metadata for a photo. When you try to locate a photo, it requires quite a few disk I/O operations. You read the file name and inode mappings, you load it, you find the inode, you read the information from the inode that point to the where the file is located on the disk, the offset, the size, etc. So it requires sometimes up to 10 disk IOs to read all the metadata information, as you can imagine. And there would also problems around like the boundaries of a read RAID, random array of some disk. I remember what I stand for, but you can see that sometimes you go across the boundaries, go across the file extent, so that would adding the extra metadata we needed to locate the file. So you may think it's fine. Yeah, it's absolutely fine if it's on a small scale or in our personal computer. But think about billions of read per day or per hour even, or millions of upload. That becomes a problem. And according to the white paper, that is the biggest bottleneck. Then it comes the novel solution about how Facebook is handling this problem by creating or inventing a simple mechanism to handle the read and write of the nature of the file I just described. Data is written once, read often, never modified, and rarely deleted. It provided such a simple system with high throughput, low latency, fault tolerant, cost effective, and simple. So that's why I like this paper from my perspective, it's worth looking into. Of course, it lacks all the details it needed to fully understand. That's why I created this video. Hopefully, I can help you to understand better if you are new to system design or don't have much experience on how such system would work and what are the different options or what are the missing details. So I think let's start by the first step about how the photo is uploaded. So when the client upload an original picture, it will send to the web server. Of course, there's a load balancing, there's an API gateway upfront, and then we'll ignore it from this video. But if you are interested, you can check my other videos about such concept. And the web server will contact a directory. So this is one of the three main components for the Haystack architecture. So this one is, in full name, it's called Haystack directory. And from the reading of the paper, it feels like it's a manager or coordinator of the whole system. It's like the brain and source of truth for the system. So it provides the logical volume to physical volume mapping and the cookies for each photo. So first explain the logical volume. It's like a logical arrangement of where the photos are stored. The physical volume is, as it suggested, the physical volume attached to the Haystack store machines. So that's the second component of the Haystack architecture. So these are physical machines that have storage volume or disk attached to it. Could be provided by RAID. This is my assumption. It could also be provided by other storage mechanisms. But those level details may not be relevant on the system design interview unless you are applying for a specific role on that side, on disk or storage that need to fine tune out that fine level expertise is required. And also here we imagine it is bare metal, but in theory it could be also be like virtual machines, if that makes sense. It can be fine-tuned, but that requires a lot of expertise in how exactly it works. So, but in general, what would be only three options? It's either bare metal, virtual machine, or container. Depends on the benchmarking or how it performs in production and how it is combined, like say, like multi-tenant to save the operation workload. Uh, but it's a design consideration. From my perspective, I believe it will just be like bare metal for the dedicated purpose. It's fine-tuned for provide a lot of storage capacity with CPU that is maybe not really so powerful, but powerful enough to provide those computing power. So here we may look into details, but what are the responsibilities for the directory? But here you need to know when the photo upload request come into the web server. Web server will communicate with directory to get a logical volume where the photo should be stored. And within that, it will also respond to physical volume address like IP or port number. So hey, you should upload the photo to these three physical volumes. And here it creates the record where it goes. The reason for that is the logical volume, I think, is static enough, static and stable enough. But the physical volumes, as we can imagine, the hardware failures, RAID failures, motherboard failures, anything can happen to the physical storage. So that might be change. That might change. That's why it's quite dynamic. Every time when we upload a photo, the web server may need to must contact the directory to get the information. Hey, what is the logical volume I would upload those photos, and what are the physical address of those volumes. And then for each photo, it generated a cookie. It didn't say in the paper like what the cookie is random generated or it is hashed or encrypted with some information. But from my perspective, I think it will be making more sense if it contains some metadata or information of the photo. So it can be used or extract later on at different layers, like the caching layer, at the store layer. We'll go into that details. Or it could possibly be just a cookie for uniqueness. And then web server will have like two options, because for each uploaded photo, we'll store it in four different size, like some name small, medium, large. It could be called other names, but definitely that Facebook stores 4 copies of each image for different size. So here it could be either like we have a queue for processing, or the web server can process it themselves, because again, serverless. It could have the power to do that. It could be having the working queues. Of course, that will be trade-off. From my perspective, I believe it is option one. Web server will handle the transcoding or transferring the image into different size by itself, saving the necessary for queuing and for workers, because I do believe from the white paper perspective, it is a synchronized process. The web server will be uploading the four size of each photo to the volumes it is provided by the directory. And then it will, only after it is successful, it will be get back to the original, the request from the client. And also from the paper, like each size of the photos, the 4 different sizes, will be stored on 3 different volumes. I do believe it's geo-based for fault tolerance to reduce the latency on retrieval. And then it comes to the question, like, who is responsible for the replication? It could be the web server uploaded to 3 different physical volumes mounted on 3 different servers in different locations, or it could be the responsibility for the Haystack store machines to do that. But from my understanding, if the Haystack store machines can do that, it will have the information of all the other Haystack machines, which diminished the benefit from the directory who is like maintains the control and the data mapping of all the physical logical volume and also the store machines, I believe. And so in this case, that kind of information is abstracted to the directory. So the Haystack store machines wouldn't have the information about like each other. It will be handled by the directory. That's why it is an abstract layer. And I think that makes sense. And so now from this image, we should know when the image is uploaded. Web server contact directory to get cookies for each photo and get the logical volume, physical volume, IP address port for the upload. It will process the photos and convert them to 4 different sizes, and then upload the set to the physical volume one by one. And again, here, that's typical design concept. If you want strong consistency or like weak consistency, you wait for one successful response from the machines, or you wait for all three to be successful, or you abort. So that's typical design choice. But here, I believe like one successful upload would be enough. Then the rest will be handled by directory for health checking, for fragmentation, for everything, and it will send the command to the machines for, hey, create another copy on this machine, etc. So it handled by the directory. I do believe it has a lot of hidden functionalities, not clearly or explicitly listed out by the white paper. But from system design perspective, we can derive those functionalities. And then move on to this picture. It has like more details. So let me open the white paper for the directory. So here, first responsibility for the stack directory is to maintain a mapping between the logical volume and the physical volume. Instead, including the current status information for each physical volume and where it belongs to, on which machine the physical volume belongs. So that kind of information is critical for the design. So logical, including IP port on which machine they are, and also status size, remaining capacity from CPU, I/O, etc. So all the basic information from a disk or storage perspective, maybe even latency, yeah, etc. Cookie generation, like we said, each time the photo server contact the stack directory, it will generate a cookie. And I do see there's another responsibility when I was reading the paper that it might need to aware of the photo IDs. Let me find where's my note if I can. So let's mark it optional. Yeah, so you can see there's a logical volume mapping to the physical volumes, and the physical volumes belongs to Haystack store machines. And here an important concept is on the read path, the photo server will contact the stack directory. I believe in this case, the main purpose is to have the information. First about like which physical store or Haystack store machine is healthy to serve this read request if it is not found on the caching layer or at the CDN layer. So that is one important concept. And the second, stack directory is responsible for load balancing between the internal cache layer and also the CDN layer, which is external caching. It says in the white paper, so it will be responsible for to determine, have a mechanism to decide the workload between the CDN and the cache store. And then the photo server will use that information to construct a URL which has information on the CDN, the cache, and the machine ID, which is the Haystack store machine layer. This is the last step or the last attempt to try to retrieve the photo that is requested by the user. So in some cases, the request will go to the CDN. CDN will check, hey, do I have that layer? Do I have that photo? If not, it will remove the first part and it knows where to contact on the caching layer. And they will pass the request to the cache layer. The cache layer will see, hey, do I have a copy of the cache? If it has, serve the request. If not, contact the Haystack store machine layer. So there's some information embedded in URL and also with logical volume and photo ID to for the store machine to identify where the photo is located and reply. We'll go into the details of Haystack cache layer later. That's for the read path and also the URL generation. And also another concept about like, hey, how the photo servers are aware of the cache layer and the Haystack store machines. It could be through like DNS, could be through like service registry. And there are quite a few possibilities, and I don't see too much difference between them by using a DNS server or by using the internal service registry to find and locate those services. So I believe it will be a design choice made by some other considerations, maybe technical stack, maybe how it fits in the meta ecosystem. So we don't need to surmise how it exactly works, but you need to provide those information to your interviewer, like in your system designs. Now here comes the Haystack cache layer. I've mentioned it a few times, but haven't actually go through that. It is like internal caching layer upfront in the physical storage of those volumes. So I think it's simple enough. It is one layer. It could be separated from those machines. It could be co-located on the machines, or it could be very close adjacent to those machines physically. But from the concept perspective, it's a logical layer. On the physical side, right located, it could be like fine-tuned internally by Meta or Facebook. So it is a layer, again, it's a cache layer. The purpose is to fast it. One of the main purpose is to fast retrieval of the photos, especially for recent photos. And then the second one is to serve to as like entry point to the physical volume, because let me explain how the caching layer works. Based on the paper, there is only two conditions where the caching layer will cache the photo. So first, the request needs to come directly from the user and not the CDN. And the second, the photo is fetched from a write-enabled store machine. So only if these two conditions are matched, the cache layer will store the copy of the photo here. So it's a cache layer. It could be in memory caching. It could be SSDs just for faster retrieval of the data. We don't have the details, but I do believe it's not necessary to be like everything in memory. It could be like fast SSD retrieval. It's given the small volume of photos we are retrieving. It could be like reuse some of the work was done previously by the on the first version, like used provided by NFS, or it could be some simple server with disk storage, fast SSDs to serve that. I do believe the reason for that, if like a CDN is missing, if the request comes from the CDN, they are missing the photo or the data, it's highly likely Haystack cache wouldn't have that information. It would be effective. It wouldn't be effective. And also, given the traffic pattern, uh, I think Meta figured out most of the read will happen to the recently read, like a new upload, like a new folder on the Facebook side or the news feed. Let's have the recency where the photo is mostly read. So it will be making sense to only catch those photos. And then another important concept is on the physical volume. It will be write enabled. And then once it reaches the limit, like either the size or take offline for operation, it will be marked as like read only. And so the caching layer will only cache the physical volume that is still like write enabled, which means it is the recency. And also, given the performance, it will make more sense if the read goes to the cache layer instead of the physical volume, while it is still accepting a write request. So in this way, it can definitely improve the performance. So I think from the system design perspective, it would be enough information on the caching layer. It will based on the traffic pattern. So either way it could work, but you need to provide it with the scenario. You need to make the trade-off. So what to cache, what not to cache. So that's the design decision. And also like the how this layer is managed, that's simple enough. It's managed by like distributed hashing table. So each cache node will have the information about or partial information about other node, about house, about the management, different things, and which photo hashed photo ID should be managed by which cache server. So this typical P2P mechanism based on this. And also, I think, given the performance requirement by Meta, I do believe there can be a front end, very thin layer to handle or to manage the cache layer upfront. So instead of like that, to remove the possibility of multiple hop when we try to read or try to locate the node who is responsible for the read request of the photo ID. So this layer will be upfront, do the hashing, and goes send request directly to the node, which would have the information. And the rest is the same. This layer doesn't handle the P2P network or the cache layers. It only have like very thin layer, very dedicated responsibility to fast route request to the node that is responsible for the photo. I listed here. If you can take a read, feel free to do so. You can pause and read it. And then I think there's some complexities or some design considerations on the machine, Haystack store machine side. So it will, like, for example, each machine provide 10 terabyte. Let's write it down. The storage, and of course, it won't be provided by just one volume. It would be 100 plus 100 gigabyte. Yeah, could manage easily manage 100 physical volumes, given the modern machines and for each volume. Well, it's nice we can consider each volume as one large file, but in production or in practice, I don't think that is um, the case because I think it's the paper suggests that just for to simplify the concept, but in reality, I do believe it have multiple files. If given 100 gigabyte volume, I would imagine each file segment would be like 5 gigabyte. That's my assumption. Could be fine-tuned. I would say anywhere between 2 to 10, depending on the actual case and benchmarking data. But let's assume it's 5 gigabyte, so that would be like 20 files for each volume, physical volume. And the main purpose for that, for the Haystack is to bypass the disk I/O to read file or photo metadata. And so here, how it does is we'll go into the files later, but you can imagine for each file, it's a super block, it's called super block, and it will have a series of needles. And the needles are where the photo is actually stored, actually stored. So instead of like writing or storing the photos one by one, it is keeps appending to one large file with a certain number of files. Could be 1,000, it could be 10,000, depending on the size. And then the file's metadata is cached. It's cached together with photo ID logical volume, so we can know with the offset with the file and the size, so we know exactly where to look into for that file or the section. In this case, it calls the needle to locate the photo and return the read response. So this part, I think, even though it is an important concept, but it's clearly explained in the white paper. Needles each represent the photo. And also needles metadata, including like cookies, photo ID, alternative ID. Alternative ID is like the file, a photo type. So ID plus photo type is unique, but the 4 different types of photo will share a photo ID. And then we can use the alternative key, which is the type like large, medium, or small, and combine them together to uniquely identify or locate a photo. So we can imagine the super block or the file like a chunk or segment. It is append only. So when the request comes in, we append the file, we update the metadata mapping in the memory, and then that's pretty much it. And for the write and for the read, of course, we go to the in-memory mapping and say, hey, what is the photo is located with the file ID, with the offset and the size. We read that entire needle, do some checking on the cookie, on the checksum, etc., and then reply with that file. So simple as that. And in memory. I do believe there's two part of the mapping. One is from a logical volume to physical volume, because the physical volume maintained or controlled by one Haystack machine. It could be only mapping to one logical volume. And also, given the fault tolerance and the reliability, I do believe the logical volume would be unique in the case. So we can say like on a single store machine, the logical volume can identify the physical volume as well. So that I think that's the first layer of caching. So logical to physical mapping. And then once we know, hey, this requires a default that a certain logical volume, now we know where on which physical volume the data will or may exist. And then for each volume, there is in memory hash table to have the mapping for the ID metadata. And as always, the memory data can be crashed, machine can be crashed, and then it's rebooted it into like fast rebuild the in-memory mappings or in-memory data. In theory, it can be read from those files, but it takes more time or longer. So there is another storage on disk called index files, which have the shortened version or just simply metadata about the mapping about the offset, but without actual photo related like metadata like the cookie header checksum or the actual data. It's just the offset ID size, etc. Enough information to rebuild the in-memory mapping when the machine is rebooted. I wouldn't spend much time on the needle structure because it's clearly explained in the white paper. It has either magic number and footer magic number, which I believe is used for bit block. If the data is crashed or corrupted, it can use to rebuild the photo data. You can look into the details on like how I think how S3 works about like how to keep the high persistency about like 10 nines after 10 nines persistency. So that on the base block side, which we don't need to go into the details. And then like some other important informations about the index file and the actual superblock is not always in sync. So one write or delete happened, the superblock and the in-memory caching is updated synchronously, and the index files is uploaded async, which means there could be possibility when a file is updated or inserted into superblock and then the machine crashed. There's possibility index file don't have the latest data. So they called the photo as orphaned, which means it doesn't have a record in the index file. But when it's rebooted, we can easily identify those cases. We find the last record in the index file and then compare with the superblock. We can simply add those missing files, missing photos. And then another thing is one deleted file. The flag is updated in the superblock, changed to deleted status, but the index file is not updated. And the in-memory mapping is synchronously updated. I think there's optimization for that part. Instead of having an actual flag date field, it simply changed update offset to 0, means that photo is deleted. But that is not reflected from the index file. I mean, the paper was written 10 years ago. I do believe now there's some mechanism, either async or sync, that will be update the index file with that kind of information. Because in case of rebuild or reboot, the memory will have incorrect data because the memory data is rebuilt from the index files. Even though even in that case, it doesn't matter, like it could rarely happens, both on the deletes that have record here and also given the combined probability, the the machine is crashed, need to reboot, and also index file missing the data. And also second part, even if the rebuild mapping doesn't have the delete size, when it reads the data from the block, it can find, hey, it reads the flag is deleted, and then it can update. And also, I believe there will be, not I believe, it says on the paper that background task will check the integrity or the complexity, completeness of the data. It will do the copy through compact process to remove the deleted files and remove the duplicated files, because it is append only when you update a file. If it's going to the same physical volume, it will append to the record, which means the two duplicated copy of data. And then if it is stored in a different physical volume, we need to delete data from this physical volume, the previous data here. So there will be backend process to remove those unnecessary spaces used. I think I've covered most of the key design concept for the Haystack architecture. But if you have any questions, please let me know. It is a complicated paper with a lot of nuances in it. I'm not sure which part you are familiar with, which part you're not familiar with. And also I tried to keep it at a high level. There are other implementation details, which I have it here with me in the note, but it's impossible to cover it in the 30 or 45 minutes video. So, and I think everyone is already familiar with me now. I'm happy to discuss technical designs with my audience or my students how it works, and we have brainstorm to figure out things. And the important thing is you need to know all the basics about how memory caching disk file system works, and then you will be more confident to design such a system. And also always remember this as a trade-off, there's a given scenario context to have the better suited solution. It's not one solution fits all. If I change the request to the sentence, which I found really beautiful written about data is written once, read often, never modified, and rarely deleted. If I change some of that, frequently modified, we might have a different design. So I think that's enough for this session. If you have anything or would like to book a private session to learn any part of the system designs or prepare for your upcoming interviews, just let me know or book directly through the link on the comment. Thank you very much for watching and see you next time.